Hello and welcome back from spring break. I hope you guys all enjoyed your time off. If you went somewhere, I'm glad you made it back safely. If you stayed here, I hope you enjoyed the nice weather that we had. This week we're going to have a series of video lessons to start out Chapter 8. And the video lessons will be 15 minutes each. And if you want to watch the video again, if I went too fast or you just missed a part or you want to kind of just reiterate what we talked about, go on the website. All the links are there so that you can revisit and rewatch the videos as needed. You should have gotten a Bigfoot's mysterious footprint problem, and on the backboard is kind of some details about that, and in the corner of the room you can see our evidence left from Bigfoot's visitation to us over spring break. That'll be kind of your problem of the week that you guys are going to work on throughout the week. It'll be due Monday, April 6th, next Monday. And so work on it throughout the week, and you can help each other if you need to, but make sure that you're showing and doing all of your own individual work. All right, so we're going to go ahead and start with Chapter 8, Lesson 1. Chapter 8, we're studying quadratic functions. So quadratic functions is going to be our theme here. And a definition of a quadratic function is here. Y equals ax squared plus bx plus c. Now, b can be any real number, c can be any real number, and a can be any real number except for 0. So I'm going to write myself a little note here. A cannot equal 0. Okay? Because if a is 0, then we're out of our x squared term, and this x squared is what makes this quadratic. So I really don't even need the b or the c as long as I have some x squared term. I don't even have to have a coefficient. I could just have one x squared, but the x squared is what makes this quadratic. So I'm going to write over here, this is the standard form. Alright, so this says circle all the equations that meet the formula for a quadratic equation. So this one here, a is y equals 3x plus 2. There's no squared term here for the x, so this is no. This one, we have negative 4 as our a. That's fine, because a just can't be 0. It can be negative. We have our x squared term, and then those are real numbers as well, so b fits. C, we need to do some things here, too, to solve it for y. So I'm going to subtract 5 from both sides. I get y equals 2x squared minus 5. I have my x squared term there. 2 is not 0, so that works. Again, we could have two terms. We could have one term, as long as you have the x squared. And then y equals a half x squared minus 5. That can be a rational number, it can be a half, it can be a decimal. As long as a is not 0, it works. So those three are quadratic. Okay, so a quadratic function must be nonlinear. So we're going to form what we call a parabola when we graph these, and you'll see a graph here at the bottom. 2, it has to be symmetrical. The graph must be symmetrical about the vertex, and we're going to really focus on that tomorrow, but I'll show you what that is today. And 3 is it must be a parabola. When you graph it must be a parabola. So this really focuses on the graphing part of it, but the graphing resembles or is a result of this x squared term happening here. Alright, so the x squared term is can actually be detected in a table by finding what we call a second common difference. Now, I've showed you guys this before, but let's revisit it. So x terms here have to have a constant rate of change. So from one x value to the next, what's my rate of change? Hopefully you said +1. Then look at my y values. My y values must have a second common difference. So it's not going to have a first rate of change. So we have 0 to 3 is +3, 3 to 8 is +5, 8 to 15 is +7, 15 to 24 is +9. Now that looks non-constant. It's not. This is not linear. It's not a constant rate of change. But a second common difference means that I'm going to take that first difference and I'm going to see the difference of the difference. So from 3 to 5 is +2, from 5 to 7 is +2, and from 7 to 9 is +2. So my second common difference, I'll call it my SCD, my second common difference is 2. So my y values have a second common difference, which makes this quadratic. So what do you notice about the pattern of the quadratic function? The y values have a second common difference. And that's what we want, so that's good. All right, so you can detect it in a table. All right, what about this next one? Now we are given some ordered pairs. Let's create a table and see if we can prove it, finding that second common difference. So my first x is 0, my first y is 6, 1 and 12, 2 and 20, and 3 and 30. Okay, so I see my x values are all plus 1, check, they have a constant rate of change. Now my y values, my first difference is plus 6, plus 8, plus 10, those are all even, so that's looking good. My second common difference, those are all plus 2. So yes, this is also quadratic. Second common difference in my y values of 2. All right, now we're going to use this table here. We're going to fill out this table using this equation here, y equals x squared minus 4. So I'm going to plug these in. So I have y equals, remember to use parentheses, negative 2 squared minus 4. Negative 2 times negative 2 is positive 4, minus 4 is 0. So my point here is x is negative 2 and y is 0. So I'm going to go ahead and graph that. Negative 2, 0. All right, let's plug in negative 1. So I have y equals negative 1 squared minus 4. Negative 1 times negative 1 is 1. Minus 4 is negative 3. So I have the point here, negative 1, negative 3. And also plot that. So negative 1, negative 3. 0. So y equals 0 squared is 0 minus 4 is negative 4. So I have 0, negative 4. So that's my y-intercept. So notice that's that last term there, my y-intercept. And 1 is y equals 1 squared. When I square 1, it's going to end up the same thing as when I had negative 1. So I have 1 minus 4, which is negative 3. So my point there is 1, negative 3. So it's actually just a reflection on the other side of my y-intercept. And then 2. Same thing's going to happen when I did negative 2. So 2 squared is 4, just like negative 2 squared is 4. Minus 4 gives me 0. So this time I have 2, 0. So I'm going to go over 2 on my x-axis and 0 on my y-axis. Sorry if you hear my phone ringing. I'm not going to go get it, but this is spring break week, so I did not have my phone turned on sound. All right, there we go. So there's our first parabola that we graphed. All right, so it looks like that U shape, and you're going to get to know that U shape a whole lot. All right, turn to the back. All right, so here are some things we can predict before you ever start to graph. Before you ever graph your quadratic function, you can predict the 1, 2, and that's it. So 2 things, the direction of the parabola by looking at A. Now remember, we have y equals ax squared plus bx plus c. So my a is my coefficient of my x squared term, and we're going to look at this a, and over here we can see if a is greater than 0, so if a is positive, it's going to open upward. If a is negative, it's going to open downward. So here we need to change this a little bit to make it y equals. I'm going to add 5x to both sides. So we get y equals 5x squared plus 2x minus 6. So here a is equal to 5. So a is 5, which is greater than 0. So this is going to be, it's positive, so it's going to open upward. And our parabola, the first one that we did, was opening upward. So that's an example of opening upward. All right, our second example, this time a is negative 4. Well, since a is negative, it's less than 0, so this is going to open downward. And this right here is an example of opening downward, so it's like the upside down U. All right, we can also predict the vertex, domain, and range by the graph. So if we're given a graph, or after we graph it, we can predict the vertex, domain, and range. So looking at this graph, the vertex is this point here where it changes over from going up to down, or it changes over from going down to up. So pretend this were tracking a ball that was thrown into the air. I threw the ball up. At some point, the force of gravity and the force that I threw the ball with come to a term of 0, and then it changes directions. We're getting some science in here. Here, maybe it's a yo-yo or something. It goes down, and the force there is 0, and then it comes back up. So the vertex is that change in direction. So this vertex here is the point -2, 6. The domain, remember the domain is our x values. And in this case, this is showing a very small portion of my parabola, but these two lines have arrows. They're going to continue going on, and they're going to stretch out really, 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 really wide and cover actually all real numbers in our domain. So all real numbers, because it's going to cover all x values. Our range is our y values, and you see here that the vertex is stopping the y values there. So the y values start at 6 and then are going to go on to -infinity. So our range here is from -infinity to +6 because the vertex is stopping the range. All right, next example, the vertex here, the change in direction, is the point 3, -3. The domain, again, is all real numbers. It will usually be until we start turning our parabolas different directions. So all real numbers. And then our range is from -3, there's our starting point, and then it's going to go on to +infinity. So -3 to +infinity. All right, and our last example here, our vertex is this point here where it changes direction, so that point is -2, 6. Our domain is all real numbers. And our range, our domain is all real numbers, our range is starting at -6 and going into +infinity. All right, and just a little recap of domain and range to remind you. Remember, the D stands for domain, and Dixie and Roy D. The I is independent. The X is our X values. Our other I is input. Remember, the E stands for whatever. We came up with some things, but I don't remember them all, so we'll just kind of cross out that E. So Dixie and then Royd is range, output, Y values, and dependent. So the Y values are dependent on the X values, if you remember all that. All right, so your homework is page 527, 22 through 38. So notice I crossed out that 44 through 38 evens. And then you're going to do 39 through 44 all, and I want you to justify each answer. That's really big. Okay, I want you to justify each answer. So you should show a lot of work there. I think I did lined paper front and back. So, and I think I tried to cram it into front and back so I wouldn't have to staple answer keys. So, but take your time, show all of your work, justify each answer for that 39 through 44 all. All right, you have the rest of class time to work on your homework, so hopefully you get a good portion of it done. Again, if you want to revisit this video, you can play it again tonight. The link is on the website. All right, see you guys tomorrow.